All right, so this is part two of our series on quantum numbers, where we take the quantum numbers in general chemistry and we break them down to their easiest and most understandable parts. All right, so this can be a really tough topic for first year chemistry students, but we're just going to break it down and talk about it in plain language. All right, so quantum numbers is kind of a, you know, strange term, but the important part here is that it gives us information about electrons, okay? So we have our positive nucleus in the center of the atom shown in blue there, and then we have electrons orbiting that nucleus, right? So the negatively charged electrons orbit that nucleus, and the quantum numbers just give us information about those electrons, all right? So we talked about the principal quantum number, and we said it had a lot to do with energy, the n principal quantum number. But we're talking about the angular momentum quantum number today. So angular momentum quantum number is denoted by this fancy L symbol here, the lowercase l. And instead of referring to energy, it's going to be referring to the shape of the orbital. And the orbital is just where the electron likes to hang out. So the shape of the orbital. So I've drawn up here a positive nucleus, and we have kind of a spherical or a circle orbital for the electron. But we also could be orbiting in different kinds of areas. So we've got some with some electrons above and below here, or maybe it could be like a clover shape or something like that, where we have 4 different areas the electron could be. And we'll talk about how the quantum numbers relate to these different shapes of orbitals, all right? So let's talk about this a little bit more math heavy, all right? So the L quantum number, the angular momentum quantum number, relates to the principal quantum number n. So how does it relate to that? It is related to the minimum and maximum values for L. So the maximum value of L, our angular momentum quantum number, is n minus 1, all right? So if n was 5, then the maximum value for L would be 4, and so on. The minimum value for L is always going to be 0. Can't have a negative value for this. We're going to say the floor is at 0 for L. So let's kind of do some practice here, and you can pause throughout to do these with me. But if n equals 1, L can only be 0, right? Because 1 minus 1 equals 0, right? Let's try it with n equals 2. What are the possible values for L? Well, we know the maximum value is n minus 1, so 2 minus 1 being 1, and the minimum value would be 0, right? And there's nothing in between on that one. All right, so let's try it for 3. The maximum L value would be n minus 1. 3 minus 1 is 2. And the minimum value would be always 0. And in between, 1 is also allowed, right? Because it's between that maximum and minimum. All right, let's try n equals 4. When we do 4 minus 1, we get 3. That's our maximum value. And our minimum value is always 0. So we can fill these in, 3, 2, 1, or 0. All right, so the possible L value is related to the principal quantum number, the n value. So just to reiterate the meaning of the L quantum number, if we have an atom and we say that the n value of an electron is equal to 3, that means that electron could be hanging out in an L equals 2 orbital, L equals 1 orbital, or an L equals 0 orbital. So we're just saying for a given n value, there's multiple orbital shapes that electron could be occupying. All right, so I want to talk a little bit more about how L relates to orbital shapes and what those shapes are, okay? So first off, I want to talk a little bit about the node, all right? So a node is a concept and is a point on a graph here where we go from a positive to a negative. We cross that barrier if this was 0. All right, so that has a lot to do with these orbital shapes, okay? So I'm going to say crossing from positive to negative or negative to positive, okay? So it's just kind of like a change in sign, okay? That's what a node is. So let's talk about how that relates to our L quantum numbers, okay? So for L equals 0, we're not going to have any angular nodes, okay? So we're going to have 0 angular nodes. What is an angular node? So if we're looking at a circle here, or you can think of it as a sphere, I'm sorry. So an angular node, let's make one here. It goes through the center of the circle, okay? And it's a portion where we have a sign change, just like we talked about in the definition before. So this means that maybe we'd have positive sign on this side of the circle and a negative sign on this side of the circle, okay? So that is the definition of a node that we're talking about here. So remember, L equals 0 has 0 angular nodes. So if we were just to draw the electron cloud or the orbital for L equals 0, it would just be a sphere, okay? There's no node, so same sign everywhere, all right? Moving on to L equals 1, we have one angular node, okay? So I'm just going to draw that through the center. It doesn't really matter where you put it, but there's one angular node. So that means on this side, we're going to have, get a better pen for that. On this side, we're going to have a negative sign. And on this side, we're going to have a positive sign. And we have that node in the middle where there's no electron density, okay? So that's the shape of the L equals 1. A lot of people draw this as kind of like a dumbbell. So like that would be the shape of our L equals 1, all right? Moving on to L equals 2, the L number is always going to be equal to the number of angular nodes. So let's draw 2 angular nodes here. And they're always going to be perpendicular to each other there, all right? So let's start off. We have our negative sign. And when we cross the node here, we flip over to our positive sign. I'll do this in green. Oh. And we cross the node again. Now we're over to the negative again. And we cross the node again. And we're over to the positive. So you'll see this one is more of like a clover leaf shape, okay, rather than 2 dumbbells, all right? Now let's go on to L equals 3. So we should have 3 angular nodes. I'll kind of draw them like this. All right, so splitting it into 6 pieces. Start off with our negative. It doesn't matter which one you start off with. Just make sure you're alternating between positive and negative. So we're crossing a node, which means we flip the sign. And notice there's no electrons along the node here. You can think no is node. All right, so just filling these in every time we cross the node. Like I said, we switch the sign. And this red is negative and the green is positive. And no worries about understanding like what would negative or positive mean physically. Just know that we're not going to have any electrons on the node and we're flipping the sign, right? Okay, so now we have some pretty weird looking shapes here, all right? But know that we found this just by understanding how the L quantum number related to the number of angular nodes, okay? All right. So you're going to hear the terms S, P, D, and F a lot in chemistry. It has a lot to do with electron configurations, the periodic table, and some properties of atoms. So let's assign the letters to each of our angular momentum quantum numbers, all right? So if an electron is in the L equals 0 angular momentum quantum number, it's going to get an S, okay? Moving on, if it's in the L equals 1, it's going to get a P, all right? If it's on the L equals 2, it's going to get a D, and if it's in the L equals 3, it's going to get an F. So if you're wondering why we call them S, P, D, and F, it's more of an experimental reason. So S stands for sharp, P stands for principal, D stands for diffuse, and F stands for fundamental. However, these don't really have anything to do with the shapes of the orbitals with the content knowledge that we have now, so I would just memorize the order S, P, D, F for 0, 1, 2, and 3. Alright, so I promised that the L quantum number had a lot to do with the periodic table, so let's kind of dive into what I meant by that. So you'll notice we have 4 color groups here highlighted in the periodic table, and if you haven't seen these color groups before, that's completely fine. We're going to talk about it today. So this red group here, and it includes the helium over here, this is the S block. So remember, S is for L equals 0, and the S block is going to include everything that's highlighted in red. So we'll just go through them all, and then we'll talk about it afterwards. All right, moving over to the yellow, this is the P block. And remember, S, P, D, F. I'm sorry, that's drawn a little poorly. S, P, D, and F. The P is going to be equal to L equals 1. All right? And if you'll notice, we're moving in a direction where we go from left to right, go to the next row, left to right. So that's why we ran into the P block after the S block, all right? If we keep doing that process, we're going to get to the blue, and this one is called the D block, all right? And the D block is where L equals 2, right? So the SPDF is 0, 1, 2, 3. And the final one we have is the F block, shown in green here. So if we remember before, the shape of the orbital is what's defined by these L quantum numbers. All right, so we've been talking a lot about the blocks, but what is the physical meaning? So the blocks tell us about the L value of the outermost electrons. In an atom. Oh, sorry. All right. So the L value of the outermost electrons in an atom is given to us by the block that an atom is in. So let's do a couple examples. So magnesium here is atomic number 12, and it's in the S block shown in red. So for the S block, remember, L is equal to 0. So that means that the furthest out electrons in magnesium, draw a little diagram here. So the furthest out electrons are going to have an L value of 0, okay? And remember, L value of 0 just means that we have a spherical orbital, right? Let's talk about another example. Now I'm looking at carbon. Carbon is in the P block, and it has an atomic number of 6, okay? So what do we think the L value is going to be for carbon, those outermost electrons? It's going to be L equals 1, right? So for the outermost electrons in carbon, the ones furthest from the nucleus, our shape is going to be that 2-lobed design, right? Because our angular node goes right through the center. How do we know there's an angular node? L is equal to 1. So there's one angular node through the center of our atom. So the outermost electrons in carbon are going to hang out in 2 different spots here. Oh, sorry, draw a pus there. These are our E's. So the outermost electrons in carbon are going to hang out in those 2 lobes. And by lobe, I just mean like the areas on either side. All right, let's check out an example in the D block. Let's look at zinc, all right? So zinc is atomic number 30, and it's found in the D block. So that means the outermost electrons are in the L equals 2 angular momentum category, right? So how many angular nodes should we have? 2 angular nodes. Let me get a different color for this. So if we have 2 angular nodes, remember we're going to have that clover shape where we have the negative sign here, positive sign here, negative sign here, and positive sign here. Okay, and remember, the sign doesn't have anything to do with the charge of the electron. That's always going to stay negative. This just helps us describe how it looks, all right? And if you're wondering, hey, I'm crossing a node here, but I'm still at the same color, we're actually crossing 2 nodes in the center, so that just flips it back to the same color. So this means electrons in the outermost shells of zinc are going to behave in this way. The shapes of their orbitals are going to be that clover-looking thing, all right? Now let's go to F. Let's look at Mendelevium. I like Mendelevium because it is named after the inventor of the periodic table. All right, so Mendelevium, the outermost electrons are going to be L equals 3. That's the angular momentum quantum number there. And L equals 3, remember, we have 3 angular nodes through the center of our atom. I'll do my best there. All right, so zooming in, we're going to have negative, positive, negative, positive, negative, and positive, right? So for the outermost electrons in the Mendelevium atom, the furthest out electrons, these are the orbital shapes that they're going to be in, the F orbital. Thank you guys for watching, and please leave any questions you have about the content below. Don't forget to subscribe to the channel because we're going to be dropping more videos about quantum numbers and general chemistry. Good luck!